All right, so looking at the generalized Hooke's law. So Hooke's law, of course, is stress equal to Young's modulus times the strain. And we also have the shear stress equal to G, the shear modulus times the shear strain. So that is also true. Now we want to be able to describe your stress, all the stresses at a point, in as few stresses as possible. So of course we've got normal stresses and shear stresses, and we've got them in 3 dimensions. So if you think in terms of normal stresses, so there will be the sigma z, sigma xx, so this is this one, sigma xx, which we will say is basically the same as sigma x. That is just the normal stress in the x direction. So it works on that plane. Then we've got sigma y and sigma z. So remember, it's the normal stress in the, say, the z direction on the plane that is perpendicular to the z direction. Okay. Then, so the normal stresses are simple. Those are the 3. But if we think of the shear stresses, it's not as simple. So first of all, we need to, so a shear stress can look like this. As we said before, your shear stress is like this. So you've got if this is your little element, you've got a shear stress in that direction, and so let's say this is x and that's y. And this is the positive x, negative x, positive y, negative y. So this shear stress over here is a shear stress in the x direction, and it lies in a certain thing. So if you look at this element, if you only have those shear stresses, what will happen to the element? It's going to, of course, rotate in the clockwise direction. And we are not looking at rotating elements. We want to, what we have is stationary things, so we have to apply this stress. And so this won't move. But then the question becomes, when is it positive? So we've got a negative shear stress and we've got a positive shear stress. Which one, how do we know when it's positive and how do you know when it's negative? So by looking at one of the shear stresses there, we can decide if it's a positive or negative shear stress. So first of all, we look at the direction. In which direction is it pointing? And then, so then we times it. So in this case, it's pointing in the positive direction. And so direction, so we've already said something about in this case, the y. Now we have to say something in terms of x. So the x, does it lie on the positive side of x or the negative side? So this one is on the positive side, that one is on the negative side of x. So again, this is positive. So that is on the which side of it lies. So that means it's a positive shear stress. So let's look at another example. For instance, this one. In terms of the direction, it's pointing in the negative direction. So it's negative. And on which side does it lie? So direction pointing, that's in terms of the x. So we have to say something about y. So on the y, which side does it lie? Does it lie on the positive or the negative side? This one lies on the positive side of y, so this is positive. So negative times positive is going to equal to negative. So that's a negative shear stress. So that's how you determine whether it's a negative or positive shear stress. And so you can see that there are then these stresses. So there's a shear stress, and of course it's going to have the same equal shear stress at the bottom. Now, okay, we'll get, so we also have to see how we name these shear stresses. Okay, so the other thing that we need to do is just define the shear diagonal. The shear diagonal is, if you look at the arrowheads of the shear stresses, so there's an arrowhead, there's an arrowhead, there's an arrowhead, and there's an arrowhead. So you draw a line through the arrowheads, and that will be your shear diagonal. Also, if you think of how this will deform, it will probably look like this. If it deforms, and so the shear diagonal over here is the longest one. This diagonal is shorter. So you see, from there to there is shorter than from there to there. So the shear diagonal is the longest one. Okay. Now back to the different stresses that we have to define. Again, as we've said, the normal stresses are easy, so they are the sigma x, sigma y, sigma z. But then, if you look at the shear stresses, so you see there's a tau z and tau yz, and there's a tau zy, there's a tau xz, tau zx, and so on. So how do we define these? We have to look at it like as the following. Tau xy, for instance, the x tells us the plane, and that will be normal to the direction. And then the y is the direction. So let's see. Tau xy. There again, there's the plane. So it's the same as the normal stress. It's the plane normal to the x direction. So there it lies on that plane, and the plane that's normal to the x direction. And it points in the y direction. So that's why you get it xy. And then we can also say that if we assume it's a small element, that tau xy is going to be equal to tau yx. So this one is going to be equal to that one. This one is going to be equal to that one. And so on. And then we end up with these 6 stresses. So this is actually sigma x, sigma y, sigma z, and then tau xy, tau xz, and tau zy. And those are the 6 stresses that define stress of a small volume element. So the 3 normal stresses and then 3 shear stresses. Oops. Okay. Then elastic stress-strain relations. So what are the relationships? First of all, we know this is Hooke's law. Stress is equal to Young's modulus times the strain. So stress in the x direction is equal to Young's modulus times the strain in the x direction. Or we can say that strain in the x direction is equal to the stress in the x direction divided by the strain, achter Young's modulus. And then if we apply, if we apply sigma x, so stress in the x direction, how does this look? Let's say we've got a rod like this. We apply a sigma x, but then of course we know it's going to elongate, and for it to elongate, the thickness or the area has to reduce in the other 2 directions. So remember, this is your z, and let's say that's the y direction. So Poisson, we said there's a ratio, so his ratio is nu, and he said that the strain in the y will be equal to the strain in the z, and that will be equal to minus nu times the strain in the x. And then if you want to put it in terms of stress, so it's minus nu sigma x divided by the Young's modulus. And then this nu is a constant for a certain metal. And then, so you can say what will be the strain in all 3 dimensions based on the stress that is applied. And of course, this stress can be applied in 3 dimensions. So there's sigma x, sigma y, and sigma z. And then you can, so for x we said this is, I showed you what we did there. And then in the same way, the effect of sigma y will be this one, and sigma z this one. So sigma x gave us a strain in the x direction, and of course this is not correct because it needs a minus nu there, and it might need a minus nu there. So if you apply a sigma y in the y direction, your normal strain will be this sigma y divided by Young's modulus. But in the other two directions, x and y, x and z, it will actually decrease in area, and so it will be a negative strain. So negative nu sigma y over Young's modulus, and the strain in the z will be negative nu times also the sigma y divided by Young's modulus. And then the same way, if we apply sigma z, the strain in the sigma z direction will be this one, sigma z divided by Young's modulus. But in the other two directions, it's in the x and the y, it will be negative nu times that, negative nu times that. And now you can write, if you have three stresses, you can say sigma x plus sigma y plus sigma z is equal to sigma x over E minus nu and so on. So you can add all of these together. All right. Then we want to look at resiliency. So resiliency of a material is a measure of the amount of energy that can be absorbed under elastic conditions and which is released completely when the loads are removed. So resiliency is given by the area underneath the curve in the elastic region. So it's half times the maximum sigma max times the strain, maximum strain. Or you can just write it in terms of maximum stress, because you know what it is in terms of if you look at Young's modulus. So that's quite important. A material with a large energy absorption is what we need for a spring. So a fairly high yield strength and maybe possibly a low Young's modulus. But typically, if for spring, you'll look at the steel if you think of automotive springs and so on, all these steel springs. Okay. Then, so that first one was just elastic response. The second type of stress-strain curve that we want to look at is elastic homogeneous plastic response. Why do we say homogeneous plastic? It means that at the point of yielding, there's not a real clear indication of your yield point. And so, and we also want to describe it in terms of the true stress and true strain. So we see a stress-strain behavior revealing elastic behavior followed by a region of homogeneous plastic deformation, and data are plotted on the basis of engineering and true stress and strain. So of course, as you know from before, there's your UTS, the ultimate tensile strength, and that's the place where it fractures, and somewhere over here would be your yield strength, sigma 0. Now, just note that, and this is probably a little bit exaggerated, but where the engineering stress reaches a maximum point, this is not true for the true stress. True, because true stress especially in the necked region, so that will be there where the neck starts to form, you find that your area becomes quite a bit smaller, and because of that your true stress actually increases. Whereas engineering stress, you only work with the original area, and that's why it then falls down, because your force that you apply becomes less and less. So this points to another fact, is that your true stress is better than your engineering stress when it comes to large deformations. Whereas in this region, probably there, you can sort of say that true strain is almost equal to your engineering strain. There's not a big difference. But as you go to larger deformations, then true strain and engineering strain are not the same. Okay, then we've got the true strain, the empirical relationship. Now, please remember, this is empirical, meaning that it's just a calculation. It's not based on fundamental, so it's just a equation that we fit to the curve. And we see that this relationship that works the best is your true strain is equal to K times the true strain to the power N, where N is your strain hardening coefficient and K is your material constant. So if your material is ideal elastic, N is equal to 1, and if N is equal to 0, it's ideal plastic. So there's no strain hardening. So it's a description in terms of what happens to strain hardening. Now it's interesting to note, iron is right here at the bottom. So iron, and if you do a low carbon steel tensile test, you'll probably get something like this. It goes into yield, you get the yield point over here, and then it just stays very flat. There's hardly any strain hardening that takes place. Whereas if you do the same with a stainless steel, you're going to find that it increases dramatically. So there's a lot of strain hardening that takes place. So N that tells you how much strain hardening takes place, and so the N is quite a useful coefficient to work with. Other thing is, in this case, it's not so easy to determine your plastic or instability, or your first of all, maybe your yield point. So you have to do the proof stress, 0.2% proof stress. Now, what does that mean? It means that you look at this, your total strain to fracture, and then you say you're going to work with 0.2%. So 0.2%, 0.2 over 100 is equal to 0.002 times your total strain. And that gives you this distance. And then get that point, and you draw a parallel line to the area, and that leads you to that point A, and that is known as your 0.2% proof stress, just to give you an idea of where the yield point is going to be. So this is the yield.